So more nomenclature of double bonds. I would just simply like to point out at first that what I've drawn here are the 4 different possibilities for how many substituents are bound to the double bond. So this would be called a mono-substituted, one substitution on the double bond. So the double bond has 4 potential places where you could put things, and if you put things on one place, not hydrogen, then this would be mono-substituted. This would be di-substituted, although as I showed you in the previous video with cis and trans, all of those would be di-substituted as well. This would be a tri-substituted case where we have 3 different substituents, and then of course having 4 different substituents means it would be tetra-substituted. It is relatively straightforward to assign cis and trans if you only have one thing bound to each side, but of course it doesn't have to be that way. So this molecule right here, you can't describe in cis and trans terms anymore because all of a sudden it has 3 substituents. Now you can talk about things relative. So the methoxy, the O-methyl, the methyl ether, I would describe as being cis to the methyl. I would describe the methyl as being trans to the other methyl, and so on. So you can use cis and trans within the molecule to define what it is that you're talking about. The O-methyl is trans to the hydrogen, and so on. But if you would like to name this compound, then you can't use cis and trans anymore because we have 3 substituents. So there's a list of rules that exist to allow you to decide what it is you're looking at and whether you should call it E or Z. And remember that the E refers to trans-like and the Z refers to cis-like. Okay, so what you do though is you mentally split the molecule in half and you only consider one half of the double bond first, and then you consider the other half and you decide. And what you're trying to do is figure out which one of these groups is higher priority, which one is more important. And there are basically 2 rules that matter, and the first rule is the highest atomic number, in other words the bigger atom, the heavier atom, is the thing that's more important. And if there's a tie, then you keep going until you come to the first point of difference. So in other words, between methyl and H, methyl is more important, it's higher priority, it's priority 1, the H would be priority 2. And then over here, an oxygen is heavier than a carbon, so the oxygen is going to win, and that would be 2. So in other words, this would be a cis-like, a Z sort of molecule, because the most important one on either side is on the same side. So in other words, this is going to end up being a Z when you name it, because the methyl, which is the more important of the 2, and the O-methyl, which is more important of these 2, are on the same side. So they are cis to each other, so this is going to end up being Z. Now let's go ahead and name this. One of the easier ways of doing this, in my opinion, would be to call this a butene first, rather than dealing with this. I would call this a substituent. This would be a methoxy. So let's go ahead and define this to be a butene. And this is going to be a 2-ene, because of regardless of how I'm going to number it, the double bond starts at the 2 position. So if I'm numbering it this way, then the double bond starts at the 2 position. But if I'm numbering it this way, then the double bond starts there, again at the 2 position. So this is going to be a but-2-ene. And then what are the substituents? Well, an H doesn't count, but an O-methyl does, and I would call this a methoxy. And that then defines that I should be numbering this according to these orange numbers, where that is carbon 1, that is carbon 2, this is carbon 3, and this is carbon 4. So this is going to be a 2-methoxy 2-butene. So 2-methoxy but-2-ene or 2-butene or whatever. And then comes the last thing, which is we need to define whether this is E or Z, and we've already done that. So you could call this a Z 2-methoxy but-2-ene. Or another way of writing it, which would be equivalent, would be 2Z 2-methoxy. And that's how you do nomenclature. If I was going to try to decide whether this is E or Z over here, now that this is a tetra-substituted situation, again, cut the molecule in half, consider the left, consider the right separately. And so rule 1 is highest atomic number at the first point of difference. Chlorine is heavier, more important than the methyl. And then over here what we have is, and again we're trying to evaluate this carbon, but here we have a CH2. So right now we're tied. A carbon with 2 hydrogens bound, and then you keep going until the next one. So right now CH2 compared to a CH2, then a CH3 compared to an oxygen. Therefore this direction is priority 1, and this direction is priority 2. This would be an example that is trans-like. It is E, because the most important group on the one side and the more most important group on the other side are opposite each other. Naming this one would be quite a bit more complicated because one would have to describe this as a pentene, and I might call it a 2-chloropentene, but then naming this side chain would be relatively challenging. This would be a substantially difficult exercise, and my advice would be take a stab at it, throw it into ChemDraw, and then see what ChemDraw comes up with. I wouldn't promise that I would get this one right, but I would probably call this a methoxymethyl group over here, or something along those lines, as a way of helping you out. Key things to keep in mind for E and Z. Fundamentally, E is the same as trans, Z is the same as cis, but the key thing to keep in mind is that you're always trying to evaluate what the highest atomic number is in order to decide which one is higher priority, the heavier atom. That allows you to decide. And when you have a tie, then you keep going until it's resolved. And if it isn't resolved, then this is undefined. It is possible to have a situation that is neither E nor Z. And when you have that, then that means you have some symmetry.